All right. Chapter 6, we're going to do half of 6-1 today. And, well, I would say like 75% of it today. We'll do a little bit tomorrow. Is over what we call confidence levels. Confidence levels will help us look at a set of data and figure out what the population parameters is. We're going to focus on the mean. So we're going to be trying to figure out what is the mean of a population, or what range of values could the mean be within when we look at these confidence levels. Now, 6-1 and 6-2, you can see just in the titles alone, are very similar. What we're going to talk about for the next couple days are confidence intervals when you know the standard deviation of the population. What we're going to talk about next week is if you do not know the standard deviation of the population. And there are two different ways to calculate an interval and different tests that we use and data values and all of those things. So for right now, everything the next couple days, we're going to be given the standard deviation of the population. All right, so we're going to start with some definitions if you want to fill those in somewhere. First definition is a point estimate. A point estimate is a single value estimate for a population parameter. The most unbiased point estimate for a population mean is the sample mean. So the most accurate, unbiased, reliable estimator for our population mean is our X bar. And we're going to be focusing all on means, so we're going to be trying to figure out. Okay. The validity of an estimation method increases when you use an unbiased estimator, because unbiased estimators do not over or underestimate the population parameter in general. As your sample size increases, the error that you will receive becomes less variable. The error becomes smaller as your sample size gets bigger, which is good. The more samples we have, the more reliable the data we're going to get, and the more accurate the estimate that we receive is. The difference between a point estimate and the actual parameter is called the sampling error. And like I said, we're going to be focusing on means. So if you are asked to find a sampling error, it's the difference between the point estimate, which for us that will be X bar, mean of the sample, minus mu, the mean of the population, will be the error. Sampling error could be positive or negative, and we'll look at that in a minute. Okay, so we're going to find some value that helps us estimate a larger value for the population. Focusing on means, X bar helps us estimate the population for mu. And that's because it is an unbiased estimator. Okay. All right, so we're going to practice finding a point estimate, which for right now is just going to be estimating the mean of a sample, or calculating the mean of the sample to help us estimate the mean of the population eventually, which we'll use this in a couple other problems today. So a researcher is collecting data about college athletic conference and its students athletes. A random sample of 40 student athletes is selected, and the number of hours spent on required athletic activities for 1 week are recorded. Find a point estimate for the population, and where that is, we're looking for the mean number of hours spent on required athletic activities for these student athletes. So if we want a point estimate for the population of, or the mean of the population, we find the mean of the sample. That's our point estimate. That's all you need to know, which we know how to do that already. It's the sum of all of our x's divided by n, the number of data values. So what's our n in this problem? 40. And I'll save you a little bit of time. When you add all these up, you get 842. Divide them. Our point estimate, or our estimate, which then we can use to figure out how close we are to the actual population mean, is approximately 21.05. Okay, so something you already know how to do. We're just calling it something new now. Any questions so far? Okay, so next thing we need to talk about is an estimate is just that. It's an estimate. It's from the sample. So what we get is an interval that helps us figure out how far off we are. What's the sampling error? What's the margin of error? An interval estimate is a range of values used to estimate that population parameter. So we don't just want to say, well, we think the mean is about 21 because we're only looking at 40 data values out of an entire population. That 21 is more than likely wrong. It's probably too high or too low. So we want to figure out, okay, what range of values does that give us? How far off could we be? And that's the interval estimate. So for example, let's look at that last problem we just talked about. It says, suppose the margin of error for the previous problem is 0.6. We're going to find the interval estimate that will help us figure out then the population mean. To find the interval estimate, you're going to take your point estimate, x bar, which was 21.05 in the last problem, and you're going to add or subtract the margin of error. In this case, our margin of error, we are being told, is 0.6. Now we'll be able to calculate that in a little bit ourselves. If I add on 0.6, I get 21.65. And if I subtract 0.6, I get 20.45. So we would say our interval estimate, and it's going to look like a point when you write it, is between 20.45, 0.6 less than our sample statistic, and 21.65, 0.6 higher than our sample statistic. If you need to graph that on a number line, it's just going to be like you graphed inequalities back in the day. You're going to have X bar, your sample in the middle, and then you're going to put parentheses on either end of the number line wherever your interval goes up or down to, whatever your highest and lowest values are. So let's pretend I count by 0.2. So if I count by 0.2, that would be 3 units to the left and 3 units to the right. And you can label everything here. My X bar in the middle, 21.05. My upper limit and my lower limit of my estimate, and then we shade between them. So that's what that would look like if we graph it. So this tells us we can approximate the mean of the population now, saying it's somewhere in this interval of numbers. Okay. Any questions there? Giving an interval estimate. All right, so let's say now we know what the mean of the population is. We know what our sample statistic was, and you want to find the sampling error. So we wrote this down a minute ago. The sampling error was our sample mean minus our population mean. And you're going to always subtract in that order. They're giving us the number line here, so we can go ahead and just use the numbers. In the first one, my sample mean is 9.5. My population mean is 8.76. We subtract. That's it. These are quick little easy problems. I get 0.74 is my sampling error. For the one at the bottom, x bar minus mu. This time it's 46.56 minus 48.14. And again, we subtract. Negative 1.56 is the sampling error. the one at the bottom. Yep.
So technically, isn't it like the absolute value? This is any
So when it says sampling error, it is going to be positive or negative. When we talk about margin of error, or we'll get some other definitions for errors in a little bit, then it's going to always be a positive number. But if you know what your mean is for both your sample and your population, we want the positive or negative because it actually tells us how far off we are and if my sample statistic was bigger or smaller. If we get a positive number, it tells me that my mean of my sample was larger, higher than the population sample or population value, and then if it's negative, it tells me it's lower. So it's nice to have that positive or negative, but in general, if it asks for like a margin of error, yes, it will always be a positive number. Okay, does that make sense, guys? Why we're getting a positive for the first one, negative for the second one? First one overestimated, second one underestimated. Okay. All right, so let's talk now about a level of confidence. A level of confidence is the probability that that interval estimate we can create contains the population parameter. So just because we create this interval doesn't guarantee that the mean of my population will actually be located in that interval. The level of confidence is going to be the probability that that mean is located in that interval. So some definitions that go along with that. If you have a level of confidence, you have critical values. Critical values are the values that separate the sample statistics that are probable from ones that are unusual. And those critical values are going to be z values on our z chart. We're going to use z sub c, and they're going to be opposites. One will be a positive z sub c, and the other will be a negative z sub c. The level of confidence you're going to be given or asked for is always going to be a percentage. The critical values are the numbers on your z chart that between those values that percent is contained. So that is the area under the curve. They will always be opposite numbers. So let's say I have a level of confidence of 95%. My critical values will be opposite z-scores where the area between them is 0.95. Or if I have a level of confidence of 80%, my critical values will be opposite z-scores where the area between them is 0.8. Now, there's common ones that we use, 90, 95, 99. Here they're giving you the positive z-score, which is the one we use more often. But you can, of course, get the negative z value just by putting a negative in front of it. They're always opposite. They are also on your chart. If you guys look at your z-scores that we've been practicing with, if you look on the side that's negative, at the very bottom, it says critical values, and it says z sub c, and it gives you critical values for 80%, 90%, 95%, and 99%. So you don't have to always be searching for these, which we'll talk about how you can if it's one that's not listed here, but these are the ones that are going to be most often used, and they're on your chart there for you. Okay. Everybody got what they need here? No, one more second. Okay, so let's look at your paper. We'll do just one example so you can kind of understand how this level of confidence percentage that we're going to have relates to our standard normal curve that we've been using. So let's say we have a 90% level of confidence. The C value that we're looking at is just that decimal, 0.90. That 90% is the area underneath the curve that's in blue there. It's the middle 90% of my standard normal curve. So 90% is located there. Now we said earlier, we were talking about this on the board, that the total area under the curve is 1, which is why when we want to complement, we do 1 minus the number. So if I want to figure out what percent is left in the tails on the yellow parts there of my standard normal curve. I do 1 minus 0.9 and I get 0.10, which means 10% of the data is going to be spread out to the left and to the right. Now, because it's a symmetric curve, it's a normally distributed curve, we can take that and divide it by 2, multiply by a half, and we can say that each region to the left and to the right is 5% or has an area of 0.05. Okay, area of this one is 0.9. Once you know what area is to the left of this tail on the left, you can then use the z values on your chart to figure out what your critical value is. So let's pretend this wasn't one that we already knew. It wasn't one that was given to us. You would find 0.05, that area, somewhere on your chart. So it's, of course, going to be in the negative z values. So look on the negative side, and you're looking for one that is closest to 0.05. And there's actually 2 on here that are really close to it. They kind of go on either side of it. If you look at negative 1.65 and negative 1.64, do you guys see they're both like 5/10,000ths away? They're right on, they're equal distance from 0.05, which is why we have a z-score, if you look at the bottom, for 90% of 1.645. We're always going to use that positive value in general, but it's 0.45 because it's between 0.4 and 0.5, where 5% of that data lies, where 5% area is to the left. Okay, so that's where they're getting these numbers from. So if it was one that you didn't have, you're going to find the area to the left of it. You can find that negative z-score from your chart, and then you can just change the sign to get the positive critical value there. So here the critical values are negative 1.645 and positive 1.645, which we're going to use in formulas then in a few minutes here. Okay. Good there? Make sense? Okay. All right, so let's figure out how to actually calculate that margin of error, because it's not something you're going to be given. Margin of error is the greatest possible distance. Now we're talking about a distance. So like Hannah mentioned earlier, it's always going to be a positive number between the point estimate and the parameter that we're estimating. And when we say parameter, remember that means population. So we're talking about the greatest distance between our sample mean and our population mean, what that could potentially be. It's the ends of those intervals that we're trying to figure out. Now, everything for this section, we are going to know the standard deviation of the population. So that piece there hinges on whether you can use this formula or not. Because we know the standard deviation of the population, this is how we calculate margin of error. It is the critical value from our z-chart. It's the positive one. That will always be a positive number, times the standard deviation of the population, divided by the square root of your number of data values, your sample size. Of course, we need to make sure that our data is either normally distributed in our population or our sample size is greater than or equal to 30 for this to all work. That's what hinges on our z-score chart being able to even be used. Make sure you have that formula written down. Then we're going to practice calculating that margin of error. How far off can we be? The bigger n gets, the smaller the margin of error, which means the bigger your sample size, the closer your estimate is going to be. Okay. All right, so let's go back to this problem we started with at the beginning here. Ooh, that didn't show up there. Did my internet go out? Hold on. All right. Here we want to, given a 95% confidence level, find the margin of error for the mean number of hours that we are seeing spent on required athletic activities. We are assuming, now we've got a little more information, the population standard deviation is 2.3 hours. All right, so important variables here. First of all, X bar that we found earlier, the sample mean, 21.05. Our level of confidence, our C value, is 0.95. Standard deviation of our population is 2.3. And then do you remember what the N was? Our sample size? 40. Right? If you have a level of confidence, you should also be able to find the z-score, the critical value that goes with that level of confidence. And 95% is a common one, so it's going to be on your chart there. You should see 1.96. When we're finding margin of error, we are always using the positive critical value. Everybody see that okay? Just on the bottom. Yes? With me? Yeah, we don't have to hunt for it. Okay. So error is our critical value, 1.96, times the population standard deviation divided by the square root of our sample size. So margin of error will be 0.7, 0.71, depending on how you round. And everything in this problem is hours that we're looking at. Okay, the mean is hours, standard deviation is hours, error is hours. All right, it says interpret the meaning. So here's what this means. We can be 95% confident. Another way to word this is there is a 95% probability that the population mean, remember that's what we're trying to estimate here, is within 0.71, so sometimes we put a plus or minus in front of that. It's either 0.71 above or 0.71 below. Hours of 21.05. Okay, so there is a 95% probability, or we are 95% confident that the population mean that we are trying to estimate is within plus or minus 0.7 hours of our sample mean that was calculated. Does that make sense? Okay. Try the next one with your partner / group. Go ahead. All right. Answer. Important values at the top. N is 1,000. Sample mean, X bar is 131.4. Standard deviation of the population, 21.2. C is 90%, your confidence level, and your critical value is 1.645 then. So your error, 1.645 times standard deviation divided by the square root of N should give you approximately 1.1 when you type that in, which means the error here from the estimation is about 1.1 minutes from the sample mean that was found, which that's a pretty small error, and that's because you've got a pretty big sample there, right? 1,000 people is a pretty decent sample, so that's why we're seeing such a small error. So what does that mean? Two ways to word this. Either there's a 90% probability, or we can be 90% confident that our population mean that we're trying to estimate here is within 1.1 minutes of that 21.2 estimate from the sample. Okay? Everybody get that 1.1 okay? Get the error? Yes? Okay. So we're going to have the samples mean, the sample statistic. We're going to have an error, and what this ultimately creates is the big idea, this confidence interval. We talked a little bit about interval already, so now we're giving it an official name. We're going to have a confidence interval if we're given a level of confidence. The confidence interval is just what we did a little bit ago. You're going to add and subtract the error to the left and the right of your sample mean, of your sample statistic, and that's going to give you a confidence interval. The lower confidence limit is the smaller one, the one below your sample statistic, and the upper confidence limit is the higher one, the one above your sample statistic. Okay, so in general, we're really just doing X bar plus or minus E is the formula that we're using here. All right, so tomorrow we're going to create confidence intervals. The last problem on your paper is really quick. We have a confidence interval, and we just want to use this to figure out what's the error and what's the mean of our sample. So if I have the upper and lower confidence limits, where is the mean of the sample in relation to those? It's right in the middle, right? Wouldn't it be a midpoint of the two? So the easiest way to get your sample mean, if you have your confidence limit, is just to find an average or a midpoint. It's the same calculation when there's only two data values. Add them up, divide by 2. So 1.71 plus 2.05 divided by 2 gives me 1.88. Then I want to find the margin of error, which remember we're looking for a positive number here. How can I use that 1.88 to help me find the margin of error?
Subtract 1.7.
Yeah, so there's two ways to do it. You could do the mean minus the lower limit, or you could do the upper limit minus the mean. Either way, it's the distance between either limit to that middle value, that mean in the middle, which in this one is going to give you 0.17 either way. Okay. Another way somebody mentioned in first period to do it is you could find the difference between the upper limit and the lower limit and then just divide it by 2, because that difference between the highest and lowest value is twice the sampling error. So you could divide it by 2 then. All right, so let's do the other one real quick to wrap it up. 21.61 plus 30.15 divided by 2. The midpoint of those two values is 25.88. And then subtract whichever way you see fit. We need to figure out 25.88 is how far from each of these limits. And you should get sampling error, margin of error, 4.27 for that one. All right, so we'll stop there for today. Tomorrow then, we've only got like 3 slides left. We're just going to put all these pieces together now and form our own confidence intervals based on some data. Okay? All right, so 5-4 Math Excel, remember, is due, I think, tomorrow night, right? So that should probably be your priority if you haven't finished that assignment yet. 6-1 is due early next week, I think, but we have a Math Excel workday coming up on Monday next week. You guys will have a little bit of time in class tomorrow to work on 6-1, and then you'll have all day on Monday as well to work on 6-1, so you'll have some time in class. All right, do the cell phone lotto.